It would only have, well, let's see. If it was, and this is where this is really tricky, but the satellite is going, or the satellite is, if you envision, it's out here and going to the right. And if it were polar, it would have to be K, and it could still be going to the right, but you wouldn't have this area right here. It would be latched onto the K axis. At least it would be circling around the Earth, hitting the K axis twice, once at North Pole, once at South Pole. So let's get rid of all those. This really is wild. So it's not polar. We'll have to come back to pro and retrograde, but actually, no, we don't have to. Let's see. Looks like we're at the top of our orbit. And the reason I can say we're at the top of it is we have no I hat and we have no K hat. We're only going J. So basically, if we were going to keep ascending somewhat, we would have some more K, but we're bottomed out. So we're at the top of our orbit, and we have no more ascendance to do because our K hat is at 0 meters per second. Okie dokie. Well, that can tell me a couple of things right now. It tells me I'm at apogee, and I'll tell you why. Here, change colors again. Eccentricity vector points towards perigee. And by the picture, we can tell that the satellite is at the opposite side of that. It's at the opposite location. So that would be apogee. And so we can come over here. We can absolutely, at least we can say we're at apogee instead of at perigee. Let's see. We're not at a node because we would have to be somewhere on I, J, or negative J. Right, that's where the satellite would have to be to actually qualify for node status. So we know we're not at a node. Trying not to clutter my picture too much. All right, we know we're not at a node. And we know we're not literally on any of the axes at the moment, right? We're not at K, we're not at I, we're not at J, like we just kind of talked about that. So we're kind of flying in between all the axes, and that's pretty typical. Are we at the North Pole or South Pole? Well, we already kind of ruled out a polar orbit. So, and you can tell by the picture, we're not actually at the North Pole because the North Pole would be positive K, the South Pole would be negative K, and the satellite is not at either of those places. So we can rule those out. So really, we've done a whole lot of just elimination, even though it feels like we're kind of uncomfortable because like it's hard to visualize, and we're not even doing the normal like picture that I taught you guys. We're just doing an IJK, kind of a trying to do a 3D on a 2D. It's okay because we don't have to know everything about the orbit. We just have to be able to eliminate some of these boxes and select some. So now our last two that we're down to are prograde and retrograde. Well, the Earth rotates eastward at 15 degrees per hour. If you remember that. And check it out. Our velocity is all to the right. It's all eastward, 15 degrees per hour. So remember, the prograde orbits have some component of their velocity that orbits, or how to put this, that, yeah, matches Earth's rotation. Or let's see, yeah. Or if I were to put this a different way, if this orbit were retrograde, its velocity would be going like this right now. That would be the retrograde, but it's not. The problem tells us it's going all to the east. So we know that we're in prograde. We are not in retrograde. So what overall, what did we say? Well, It's a prograde orbit, and it's currently at apogee, and more than that, there's not much to this orbit. So there you go.
Thank you, sir.
Does that make sense?
Yes, sir.
All right, cool, man. Yeah, you're welcome. I'm gonna go get my charging cable real quick. I don't want the iPad to die. Okay. All right, I'm all charged, or should be good to go anyway. All right, what's next? Let's see here. Anybody on who has a particular question?
Sir, I have a question.
Sure.
It's in regards to launch velocities, and when doing our burnout, how do we know whether the problem is like if we're calculating our burnout, do we assume that it always will be circular? And if not, like what equation do we use, or how do we find out that it's not circular? And what equation do we use to calculate our burnout for a launch velocities equation? I
Okay,
think
good
question 17
on the review.
on the review.
Yeah, okay. All right. What is, let's look. Looks like this problem refers to like the previous couple. Given in problem 14 above, calculate delta V design required to reach the desired orbit. Okay. Let me kind of work through top to bottom, and hopefully we kind of come across that answer.
Perfect, thank you.
You bet. Okay, so let's see. It says out of Cape Canaveral, okay, so 28.5 north. That's what we really need out of that. We don't need the latitude, or the longitude rather. 80 degrees west doesn't really matter, but write it down there anyway. Altitude of 1,000 kilometers. Okay. Circular orbit. Okay. So that, and it said inclination is 60. Okay. Ran of 0. How many launch opportunities do you have? All right. That was that part. All right. So equation sheet and calculator. Let's see. The first thing to kind of note is we want to go through, ultimately we're going to want delta V needed in the south direction, right? S hat, delta V needed in the east hat direction, and delta V needed zenith. That's kind of our little matrix there. That's going to equal, as you were talking about, negative V and burnout, cosine phi, cosine beta, which we'll need to get from above, but see VBO, cosine phi, sine beta, VBO, sine phi. Okay, minus 0, velocity of the launch site, 0, plus 0, 0, V loss is due to gravity. All right, So this kind of gets to your point. VBO. This, let's see, this problem says that we are launching into a circular orbit. So that means that your RBO is going to equal essentially the A of your orbit. The reason is it has no apogee and it has no perigee. So the way that this problem could be more challenging is if it said we're burning out at perigee. And in that case, you would use, well, I'll tell you what, here, let's start off just with RBO. Finding out where we burn out, where the main engine's cut off, MECO as they call it. If you were told that you were going to burn out at perigee, you would use this equation. You might say to yourself, well, how do I know what the semi major axis is? Well, we'd have to tell you. We'd have to give you that value and the eccentricity. But then you could, your radius at perigee would be your RBO. Or if they said you're burning out at apogee, then you would use this bad boy, and that would be your RBO. And we'd have to tell you that too. But I can tell you all you'd ever see for this problem is you're burning out at perigee or apogee or a radius of a circular orbit. And that's what we have here. And so that'll be our RBO. Would you like to see the rest of the problem, or did that kind of answer your question? I guess we may as well work it out. But
We can work it out if that helps other students.
okay, cool. We'll work it out. We can work it out. Can work it out. Beatles. Okay. So velocity at burnout is going to be the same velocity as we have for the rest of the orbit. So that's just the good old mu over r. In this case, what's our r? Well, I want to just do that math real quick. They gave us an altitude, but that's not the whole story. Got to add the radius of the Earth. Cool. So now we can dive into this. I'm going to zoom in. Over 7378.137. Beep boop. Okay. Calculating 5 by 7378.137. Square root of the answer 7.35. That's all. Okay. All right. Phi. How do I know what phi is? Well, that's called flight path angle, and it is 0 degrees almost always in this course unless we give you something else. But I've only ever seen it be 0, and the reason is because, just as a quick review, if you had an elliptical orbit, flight path angle is basically if you have your r vector here, the satellite's going this velocity vector here. Phi is this angle between them. So we tell you, instead of making that be what it is, we usually tell you, hey, you're going to burn out at apogee or perigee. Yeah. Or in a circular orbit. And so in those cases, your velocity is exactly perpendicular to your r vector. And so you'll have a flight path angle of 0, although now I'm trying to remember why exactly it's 0 there, because that looks like 90. But yeah, I might have drawn phi wrong, as I recall. I'm not an aerodynamics guy. I'm not a flight path aero dude. But any event, I can tell you for sure that if you're burning out at apogee or perigee, or you're burning out into a circular orbit, that's 0. So all right, cool. Sweet. All right, well, now we have VBO, we have phi, beta. We're going to have to go and work out at least part of this previous problem to get beta. So let's see. Sine of gamma equals cosine of that over cosine of that. What's that? Auxiliary flight path angle or something. I forget. Okay. But we'll find gamma, and that'll give us beta real quick. We would have found this out if we had done this problem. If I had done this problem from scratch, and that's okay. So alpha is 60, because that's the same as inclination. And then the latitude of the launch site is 28.5. Let's see what that comes out to. It looks like 34.677 degrees. And then they say, obviously, beta of the ascending node is gamma. So that equals 34.677. Ran of 0. Huh, okay. I'm not sure which beta they want us to use, ascending node or descending node, but we'll use the ascending node by default.
So isn't it given in the question, launch azimuth is 35 degrees on number 17?
Oh, did I skip right past it? Oh, yeah, I did. Oh, thanks. Yeah, well, hey, we were right. 34.677 rounds up to 35. Ha! Thanks. Yeah, I read right past that. So, okay, so we'll assume they're beta. That's good to know. Otherwise, we'd have to know if it was ascending node or descending node from that previous problem. Okay, and then we have that. All right, now velocity of a launch site. Let's get that real quick. So they tell us that this is 0.4651 cosine L naught. 4651 cosine 28.5. That equals 4651 cosine 28.5. Okay, 0.409 kilometers per second. Okay, so we have that now. I'm just kind of marking them off as we go. All right, loss due to gravity is always a little bit more beefy, so I'm going to actually do it under this equation down here. Loss due to gravity. All right, here we go. 2 mu RBO minus R launch site over RBO times R launch site. No problem. We can do it. And let's see. Okay, RBO we discovered was right here, 738, 378 rather. Minus the radius of the launch site. So what that's referring to is how high up above the Earth, the center of the Earth, I should say, is the launch site, right? So, or put another way, we're launching from, is it Cape Canaveral, I think? Let's see. Yeah. Cape Canaveral is right at sea level. It's right on the coast of Florida, obviously. So it's not like it's on a mountain in the Himalayas. It's not like we're launching from an aircraft. I saw that on an old GR, but I haven't seen it since. Like we were launching from a Boeing 747 or whatever. But no, so we're not doing that here. We're launching from the ground at sea level. So that means, what's the radius of the center of the Earth all the way up to the surface? You guys know that. 6378.137. Okay, 7378.137 minus, oh, not minus, times. My bad. All right, now plug and chug time. Square root of that. I get 4.116 kilometers per second. Hopefully my public math is right. All right, cool. So we've got it all now. All right, let's do each of these components in turn. So negative VBO, what did we find out was VBO? We found it was 7.35. cosine of 0, cosine of 35. 7.35 cosine 0, sine 35, 7.35 sine 0. Okay, minus velocity of our launch site, which what did we find that was 0.409. Okay, 0.4090 plus 0, 0, 4.116. All right, sweet. So in the S direction, zoom in here, we're going to have 7.35 times cosine 35, negative 6.02 minus 0 minus plus 0. So, okay, 7.35 now times sine 35 minus 0.409. 3.807, and then let's see, 7.35 times sine of 0, oh, that's 0, minus 0 plus 4.116, so 4.116. Okay. All right, we're almost there. So that's delta V needed in each of your 3 directions. Delta V design is the magnitude of that vector plus losses due, or losses other than gravity, OTG. What they say that was 1 kilometer a second? Yeah, cool. So square root of negative 6.02 squared plus 3.807 squared plus 4.116 squared plus 1. All right, a little bit of calculatoring here. Here, 0.6.02 squared. There we go. So that's 8.226 plus another 1 is our 9.226 kilometers per second. Woo. We did it. Nice. Okay, cool. So that was a long answer to your question, but let's see. Let me check the chat. I think I see somebody come up in the chat. Ooh, number 38 on the review packet. And yes, Cadet Toussaint, I see. I'm recording this and I'll post this in the channel afterwards for sure. And number 38 on the review packet. Okay. All right. Yes. Interplanetary. I assume this is a one that folks might want to see. That'd be good. Okay. I'm going to hear some crinkling. I'm open up a granola bar as I'm talking here. You are sending an interplanetary probe from Earth to Venus. Assume parking orbits around each planet are circular, and the planet's orbit around planets, plural, orbits around the sun are circular. R to Venus, R to Earth, mu Sun, mu Venus, mu Earth. Don't forget mu Earth. Okay. And how long will this trip take? Alrighty. Zooming in. Whenever someone says how long will this trip take, I immediately think time of flight. Okay. And for home and transfer or interplanetary travel, which this is, we take the period of our orbit, of our transfer orbit, and we divide by 2 because we hope to only spend half of that transfer orbit actually in the orbit. So actually, let me back up. The period equation is two pi a cubed over mu, and we're going to have to find what that a is because that's the wow, that's bad. try to write a little t. There we go. Semi-major axis of the transfer orbit. We're gonna have to find that first. So I think what might help is for you to draw a picture. Okay, here's the sun. Here comes the sun. And we have Venus orbit and Earth orbit, which is actually farther out, but for the problem, it doesn't matter. So we're going to go from Earth to Venus, and that's Venus, and it has like a, here, I'll make it like that, it has like a hazy atmosphere, whatever. Okay, cool. And we're going to enter a parking orbit around Venus, and Venus is going to have a sphere of influence around it. Same for Earth. We're going to start off in a parking orbit around Earth, and we have the sphere of influence around Earth. Okay, so our path is going to look something like, we'll do a burn right here and a burn right here. So that first burn will be delta V boost. Whoa, how did it do that? Delta V boost. The burn over here will be called delta V retro. That's what we call them. And that'll get, the boost will get us started on our path. And then when we exit the Earth's sphere of influence, we'll be going a speed of what we call V infinity at Earth. And in interplanetary space, we're mostly governed by the sun. And then when we hit Venus's sphere of influence, we're going to be going a speed of V infinity at Venus. That's just a little symbol. And then we'll enter our parking orbit and do that final burn. Okay, so that's just kind of where the different velocities are going to happen. We'll be going Vpark there, and we'll be going Vpark that there. All right. So having said all that, what's the semi-major axis of this transfer orbit? Well, the radius of the Earth to Venus and the radius of the Earth to the Sun are the two kind of, what would you say, two parts of the transfer orbit, because there's the radius of the Earth to Venus, there's the radius of the Earth, or sorry, Sun to Venus, there's Sun to Earth. And so the semi-major axis of our transfer orbit is that whole thing right there. I'm going to get rid of that. So let's add our Sun to Venus plus our Sun to Earth divided by 2. And that'll give us our semi-major axis of that transfer orbit. What do they say? 1.086 times 10 to the 8th plus 1.496 times 10 to the 8th over 2. Let's see what that comes out to. Okay. So if our period is 2 pi, and time of flight is half that, remember that, excuse me, remember that for most of our orbit, we're orbiting the sun. The probe, as soon as it exits Earth's sphere of influence, is pretty much traveling around the sun more than anything else. That's why we use mu of the sun. Okay, I get this to be 1.265 like million seconds. No. Yes. 12.65 million. Whatever. You can circle that and call it good, because the problem doesn't say put it in days or years, but I always put it in days because it doesn't make any sense to me at that many seconds. So just for fun, problem didn't say to do this, but I'm just doing it. Ends up being like 146 days. It's a long time. Not as long as Earth to Saturn or something like that, though. Okay. Sorry, sipping on some coffee here. All right, so what's the delta V boost required to depart Earth? Well, all right. Equation sheet kind of, I don't want to say it muddies the waters, but it doesn't lead you through quite as like directly as some of the other problems that we have in the course. And that's okay. But to get delta V boost, we're going to need a few ingredients. We're going to need to find Vpark, V hyperbolic, the velocity of the planet itself around the sun, planet it's supposed to say, and V transfer at the planet. In fact, I'm going to construct this in a slightly different way, so hopefully it becomes a little more checklisty and easy to visualize. Step one. I'll write it over here. Step one, we're going to find the velocity of Earth going around the sun. Step two, we're going to find the velocity of transfer at Earth. That's the speed we're going right after we burn. Step three, find out how fast we're going in our parking orbit. And step four, we'll find that excess hyperbolic velocity at Earth. These two things up here give us our V infinity at Earth. And running out of space, but that's going to give us our epsilon infinity, and epsilon infinity is what we use ultimately to get some of the stuff in delta V boost. So it's all going to go in, the pot. But let's start one thing at a time here. All right, the velocity of Earth around the sun. Well, we're going to assume the Earth's orbit, even though I drew it, terribly like an egg, we're going to assume it's a perfect circle. So go ahead and use that mu over r equation. But which mu and which r? Well, the Earth is going around the sun, and the radius of its orbit is the radius of sun to Earth, as I called it, S to E. Isn't that what I called it? I used a little symbol. I'm going to use the letter. Yeah, S to E. Okay, so mu of the sun, 327 times 10 to the 11th, over radius of sun to Earth, which is 1.496 times 10 to the 8th. And 6, 8. So the Earth is going 29.783 kilometers per second around the sun. That is pretty fast. Okay. So after we do our first burn, we're going to be going speed of V transfer at Earth. And so that's going to be the start of our, transfer orbit, which is an elliptical orbit, which means we're going to use the 2 mu over r plus epsilon. And then, of course, epsilon is going to be negative mu over 2a of the transfer orbit. So let's plug and chug. And remember, we're still talking about orbiting around the sun at the distance of sun to the Earth. Okay. All right, 2 times mu of the sun over radius of Earth to sun, 1.496 10 to the 8th, minus 1.327 times 10 to the 11th over 2 times, what was a of the transfer orbit again? Let's see, 1.291 times 10 to the 8th. Cool. Let's see what that is. Times 2 square root of the answer. Wait, really? That makes sense, I guess. 27.316 kilometers per second. Okay. All right, cool. So we found velocity of Earth around the sun, and then the velocity of our transfer around the sun with respect to the sun after we do our burn. That's good. All right, now let's get V infinity out of that, because V infinity is a component that we need to get the rest of the problem. So V infinity at Earth, remember, that's the speed we're going right here when we exit the Earth's sphere of influence. So that's just the absolute value of V at Earth minus V transfer Earth. Stop. 29.783. Wow, there we go. Minus 27.316. Okay, I get that is 2.467 kilometers per second. Cool, V infinity to Earth. All right, now we'll shelve that for a second and talk about the probe itself, because we were kind of doing everything like velocity of Earth, V transfer Earth. You are doing basically a top view of the solar system centered on the sun, and everything is sun-centered. But now we have to do a second component of this, and that's finding out how fast the probe itself is going around the planet before it exits, and then how much excess hyperbolic velocity do we have to add for this burn. So V hyperbolic is. All right, one crisis at a time. Vpark around Earth. Okay, so the probe is going around Earth when it starts off. Sorry. We're running out of space for something like this. There, that should be Earth, and its radius of its parking orbit around Earth is the R we're going to use. So let's see. Vpark. What was Vpark at Earth? 6978. Cool. Okay, I get that we're going 7.558 kilometers a second around Earth. And V hyperbolic. Okay, this is a little bit interesting because this is a different somewhat equation than you've seen before. Square root of 2 mu of Earth over Vpark plus epsilon infinity. What is epsilon infinity? Well, equation sheet tells us epsilon infinity is V infinity of that planet squared over 2. Huh, that's a little different, but that's okay. We have V infinity. We just found it down here. Cool. So 2 times 398,600.5 over 6978 plus V infinity Earth 2.467. Stop. There we go. Two. All right, let's see what that comes out to. Times 2 square root. Yeehaw. 10.97 I get. 97 kilometers per second. That's V hype. All right, well, delta V boost, we are told, this is the final thing we actually wanted here. right? Delta V boost is what they asked us for. Is absolute value of Vpark minus V hype at Earth. And let's just do that real quick. 7.558 minus 10.97. 3.412 kilometers per second. Circle it, call it. Okay, that's how much we need to get started on our journey. That's delta V boost. So we found that. What else does it want? Retro. Okay. Well, let's see. You know what? We'll just do this in blue. I know we did Earth in red, but we'll do this in blue. No, we'll do it in red. No, we'll do it in blue. Okay. What's delta V retro required upon arrival at Venus? All right, so we're going to repeat this entire process from up here. I'm going to write it out. So first step, we're going to find how fast Venus is going around the sun. Then we're going to find our transfer speed, which is right before we do our burn at Venus. Then we're going to find, actually, I guess then we'll find V infinity at Venus. Then we find Vpark, parking orbit around Venus. And then we'll find out V hype at Venus, which is the excess hyperbolic velocity again. And then, right, these things will all go into, that was terrible, but V retro, delta V retro. Okay, so basically it's repeating the process with Venus's numbers. Meh. Let's just do it. Okay, velocity of Venus itself around the sun is going to be mu of the sun over radius of sun to Venus. How far is it from Venus to sun? 1.086 times 10 to the 8th. All right, let's see. Wow, 34.956. That's fast. It's going fast. Okay, V transfer at Venus. So right before we do our burn, equals 2 mu sun over radius of sun out to Venus. Yeah, minus, well, plus epsilon, but epsilon's negative mu over 2a of the transfer orbit. Okay, so we can probably plug and chug that. Over 1.086, supposed to be a decimal. 10 to the 8th minus 1.327 times 10 to the 11th. Shoot, what was that? Calculated that a while ago. 1.291 times 10 to the 8th. Whew. This is quite the involved process, isn't it? 1.086 E8. Boom. Minus 0.327 E11 by 2.291 E8 times 2. Whew. Square root of that, really, is 37.629 kilometers a second. Okay, so remember, this is just our process of getting V infinity right here. So let's get V infinity. It's the absolute value difference between those two bad boys. 34.956 minus 37.629. 2.673 kilometers a second is V infinity at Saturn. or Saturn. Wow, Venus. What am I even saying? Okay, cool. Actually, I don't really want to circle that. It didn't ask for that. That's just part of the process. Okay. All right, next. Vpark around Venus. Let us do that. Vpark. So once we get to Venus, how far out are we going to be around Venus? Well, let's see. We're going to do mu of Venus, which they gave us, over our park at Venus. So I don't know those off the top of my head. Let's see. Mu of Venus is 3.249 times 10 to the fifth. Over what? Our park Venus. 6552. Let's see. Good. Okay, looks all good. All right, 3.249 E5. Boom. 5 by 6552. Boom. Screw that. 7.042 kilometers per second. Okay, fine. Now we got to find the excess hyperbolic velocity around Venus. Or sorry, to get to Venus. My bad. I'm really going to have to zoom in here. 2 mu of Venus over our park Venus. Epsilon infinity, which, as you guys remember, is here. V squared over 2. But in this case, it's V infinity at Venus, which we just found. So instead of Earth, 2 times 3.249 times 10 to the fifth over 6552 kilometers plus 2.673 squared over 2, because that's V infinity at Saturn, or gosh dang it, V infinity at Venus, which we just found. .249 E5 by 6552 plus 2.673 squared divided by 2 times 2, 10.311. All right, we're almost there, guys. Delta V retro, which is what this problem really wanted. Absolute value of V park at Venus minus V hyperbolic at Venus. Oof. Okay, running very low on space, but that's okay. We're almost done. 7.042 minus 10.311 delta V retro equals 3.269 kilometers a second. All right. That's a serious problem, right? That's a serious math problem. You're not messing around. Okay, I want to add one more thing to this. They didn't ask for this, but it's common to ask for this. If we said, what's delta V design for this mission? You would just add up delta V retro. Oh, well, why not delta V boost first? Delta V boost plus delta V retro, right? If they just wanted the total delta V or the total delta V design, same thing. You would just add the two things that we found, right? 3.412, 3.269. All right. All right. It's been about an hour. I'm going to take a quick break. Be back around 20 minutes after the hour, and I'll just leave the chat channel up and the Teams channel up, and I'll be right back.
Awesome. I had a question. It's from the GR. I could share my screen to show you, but I just wanted to clarify, like, what was wet mass, dry mass, and payload mass.
Yeah. Okay.
Sure. Let me share my screen. Can you see this, sir?
Let's see. Yep, I got it.
Yeah, and so like problems like this, and then I guess also as well with the EPS problem right after.
Okay, actually, no problem. So what I'll do is let me share my screen again, and I'll pull up the GR just fresh, and we can go through it. How about that?
Sounds great, sir.
Okay, mode sensing. This is from the GR3. Has following mass budget. What's wet mass, dry mass, and the mass of the payload? Okay. This is, I mean, for all the stuff I wanted to pull up here, or all the work I went through trying to get this pulled up. Sorry, it's actually a really simple problem. So the dry mass is the whole satellite except for the propellant mass. Wet mass is the whole satellite, including propellant mass. No. Go back. Here, you know what? I'm going to make a little change here. Tilt. There we go. Including propellant mass. All right, so let's see. What do they give us here? Structure. Oh, all the systems, right? All the things. Now, what is the satellite doing? It's doing remote sensing, so it's taking pictures from orbit. That means that the camera is its payload. The payload is the thing that does the thing that you want it to do. Like, or let me put it a little better. I won't launch a satellite just for funsies. It has to have a particular purpose to pay all that money and go through all the pain of doing that. So the payload is the actual component that does the unique mission of the satellite. In this case, it's taking pictures. Like in GPS's case, it's a clock, a very precise clock on board the satellite that, then we can broadcast out that timestamp. For communication satellites, it's a specific payload that receives signals and rebroadcasts them. So like it's whatever specific special piece of machinery does the mission, that's the payload. Okay, so we can actually write down the payload mass right away. They said that was 80 kilograms. Simple. That's pretty much it right there. Okay, now let's do wet mass, dry mass. So wet mass is going to be all of this, and dry mass is going to be everything except for propellant, right? So, okay. So let's do dry mass first. That would be here. 150 plus 20 plus 30 plus 50 plus 60 plus 30 plus 80. 50 plus. Okay, that looks to me like 420. 420 kilograms. And then wet mass is just going to add that plus 90 more. That's going to be what, 510? Ta-da! Thoughts on that?
Sir, and then for fundamental frequency, it's just dry mass, correct?
No. So fundamental frequency, thinking about kind of the overall story, fundamental frequency matters the most by far during launch, right? And so when you launch your satellite, do you have the fuel on board? Let me ask you that.
Yes.
Yes. So yeah, for F fund, like when you're doing those calculations, you want to use the wet mass for sure. Okay. So whoever was asking about the rest of the problems, I think was it Andrew Rorka? But I'm not sure. Do you want me to keep going here or?
Oh, that was good. That was good, sir.
It was you. Okay, cool. All right, sounds good. All right, what's next then? Go back to the review packet. Anybody have particular questions? Okay. Well, what we could do, just kind of start.
Sir, somebody asked on the chat for number 27 on the final review.
Thank you. That's what I get for minimizing the chat window. Oops. Oh, I see it now. Number 27 on the final review. Now I'll leave this up on my computer so I can see. Okay. Oh, show me all the messages. There we go. Oh, we got, signal noise. Yes, this is, love it. Okay. Let's see. Almost there. Okay, this one. Common data handling subsystem. So, and I see Lawson, I guess, is who asked this question. When I do signal noise ratios, I get a ridiculously large number. Can we cover one of those really quickly? Absolutely. What I suspect is going wrong is we want to make sure that we're entering our max, or, well, if it's best case, we're going to use just height above the ground. But let me draw it out and I'll show you what I mean. But the first thing, and I think I know why it's happening to you to get a big number, is we want to make sure we convert everything into its most basic units for this type of problem. Like the signal noise equation doesn't handle kilometers well. It doesn't take megahertz. It doesn't take, everything has to be in hertz, Kelvin, watts. Thankfully that already is in watts, and meters, right? So meters, not kilometers. You have to put everything in its most basic unit. So this problem says satellites in a circular orbit with an altitude of 750. Okay. Calculate the best case signal to noise ratio given the specifications below. I want to do best case, and I think I want to do worst case with you guys. So I'll show you both, because there's a critical difference between them. But let's start off with that. So let's see here. Here's the Earth. We have our little ground station. And the satellite is orbiting the Earth, and it's going this direction. Cool. So when the satellite first rises up above the horizon, that's the first time you can see it. It's really far out. It's very distant. We call that our max. So it's like, how to put this? It's the farthest away from the ground station the satellite is going to be throughout its path, because as it gets closer and closer, it eventually is going to be directly overhead. And that's going to be pretty, that's going to be clutch, right? We could just use its height above the ground as the radius there. So basically, that's the best case. When it's directly overhead is by far the best. The worst case is our max, because again, as the satellite gets closer, that distance between is going to get smaller and smaller and smaller. And that's great. That's a good thing. So anyway, if they said worst case here, we would use the R max equation, and that's what I'm going to show you guys in a second. But let's just follow what the problem says and calculate best case SNR for now. All right. So let's follow my advice that I gave to myself and convert everything to its most basic units. So bandwidth needs to be in hertz, not megahertz. So that's 1 times 10 to the 6th hertz. 20 degrees Celsius, we need to convert to Kelvin. So I'll add that 273.15 plus 20. So our temp's 293. Gain is unitless, so that's good. Transmission frequency. Okay, this is good, but we're going to have to use the conversion on the front page of the equation sheet on remote sensing to give us our wavelength instead of our frequency. Oh, oops. Why did I write that on top? There we go. Speed of light's 3.0 times 10 to the 8 meters per second over the frequency they gave us, which is 3.0 times 10 to the 9th hertz. Oh, that's convenient. 0.1 meters. All right. Okay, now I think we have everything we need. So let's start. Let's put in the equation. It says, let's see. S over N. It's the power of the transmitter times the gain of the transmitter over K, which is that constant that we're given, times the bandwidth, times the wavelength over 4 times pi times R. Well, oops, almost said R max, but it says best case. So right now I'm just going to cross that out and say we're going to use the height there. Excuse me, squared times the gain of the receiver over the temperature. Okay, no biggie. Let's see, power of transmitter 18 watts. Gain of the transmitter 5. All over. Oh, this is going to be long. 1.381 times 10 to the negative 23rd. Bandwidth, which is 1 times 10 to the 6th hertz. Okay, times 0.1 meters. Remember, it has to be meters over 4 pi. Now, how high up above the ground are we? Well, an altitude of 750 means when it's directly overhead, it's 750 kilometers away. So let's convert it to meters. We have to. And I think that's what gives, like I graded this problem on the GR for GR3, and that was the problem that it gave people like massive, blindingly huge S over N. Is that they put in the radius max, or if it was height, they put it in kilometers, not meters, because you're dividing by a much smaller thing if you use kilometers.
Sir, what was B again?
What was B? Bandwidth. Right here.
Thanks.
You bet. Let's see. So the gain of the receiver is 3 over the temperature of 29 or 3.15. Okay. Doing a quick check before we even put it in. Let's see. Gain, power. Okay, everything is in its correct units. So here's another thing that causes a problem. Don't forget to square. Got to square that. Okay. All right. 18 times 5. 1.381 e negative 23. Let's see. 6. Boom. Okay, so this first term, 6.517 to the 18th. The second term here, 0.1 divided by 4 pi, 750,000 squared. 1.12, wow, be better than that. Oh, 1.126 times 10 to the negative 16 times oh no. Zero 102. Okay, let's see what all that is. One. This one's a little tedious, but no iteration or anything crazy like that, so could be worse. Oh, brother. Parentheses management, that's another thing that gets people like me. 01. 02. Okay. Oh, this is not so bad. I get 7.484. That's pretty good. Is that right? Yeah, I think that is right. Ta-da! Should probably pull up the key just to make sure I'm not super off. Yeah, oh, pretty close. I think, yeah, what we see with these keys, yeah, they say 7.5, 7.44. I'm pretty close. Because I took the 3 terms instead of just keeping all the, whatever, a little bit of a rounding error on my calculator instead of using Excel. Cool. Now, the only difference, again, would be if they said worst case, we would replace height. So instead, we'd use our max. And the reason that matters is, so our max square root of the radius of the Earth plus the altitude, or h, squared minus radius of the Earth squared. This gave folks a lot of problems because people would put in radius of the Earth here, and they'd also put in, they would add radius of the Earth plus altitude for that, instead of just adding the altitude for that. That makes sense. So it ended up being like 6378 plus 7378 squared minus r, and that gave them ridiculously tiny numbers at the end because you're adding in way too much right there. So anyway, that's what would be different if they said worst case, you'd use r max instead of height. And again, plug in meters. All right.
Wait, so could you repeat that part where you add in? You're not supposed to add in when for the plus h?
Yeah, so I mean, basically just follow the equation, because here's what people did wrong, and this is what I was trying to sort of show. People would add in the radius of the Earth and the altitude. That's what you should do. It should be radius of the Earth plus altitude. Instead, what folks did was people would add in the radius of the Earth for that part, and then they would add radius of the Earth again plus the height instead of just adding the height. That's not correct. That adds up to way huge of a number. Way too big.
Raj, thank you.
You bet.
Sir. So when you're given, like on the GR, it gave us the semi-major axis instead. So that's already, and it was circular, so that is already the radius of the Earth plus the height, correct?
Yeah, that would be this entire term. Yeah.
Okay.
I saw one very evil old GR where they didn't give you a circular orbit, and so that wouldn't necessarily be true for that. But I've never seen it ever since. And that was many, many years ago, so wouldn't sweat it. It's going to be a circular orbit, I could almost guarantee. Okay. Signal noise, very good question. Sorry for my allergies. What's next?
Could we maybe go through the ballistic missile questions on the review?
Yeah, faux show. Okay, let's see. Oop, keep going down, keep going down. Okay. In order to ensure that our ballistic missiles are fully operational, I'm going to have to zoom in. This is, well, sorry for rotating my iPad over and over. Sometimes it's easier for the orientation. Yeah, okay, we periodically, that's actually not Air Force Space Command. This is super old. Global Strike now. But anyway, that doesn't matter for the problem. They conduct test launches to ensure missiles have been stored in the silos in the performance plan. This is true, and like they'll release like a press release to the whole world saying, "Hey, look, we launched one of our old, not all, I mean they are kind of old, but one of our ICBMs out of a test silo out at Vandenberg, and the rest of the world watches and basically sees that it hits our dummy target. We obviously take the nuclear payload out, and they're basically it's us proving to the world and to ourselves that our ICBMs are still a totally credible deterrent. So anyway, that's the history. We do this very frequently. They want to know what the range angle to launch a Minuteman III from Vandenberg on the west coast there to the Kwajalein Atoll, which is a little tiny like coral reef chain or whatever out in the Pacific. But we have a lot of stuff there. It's a U.S. Territory, possession. I'd have to have my poli-sci folks help me out with the actual term, but yeah. Alrighty, so going to my ballistic missiles area of my equation sheet. We have this kind of long equation, and I'm just going to write it all the way out here. So cosine of capital lambda, which is what that little TP kind of looking symbol is sine of L naught, sine of L target, plus cosine L naught, cosine L target, big L, times the cosine of delta small l. All right, so what might help is if I label this stuff a little bit. So the O, the origin, O stands for origin. So our origin is, here's the latitude. Big L means latitude of the origin. This is the longitude of the origin. This is the latitude of the target. This is the longitude of the target. Okay, so we're launching from west to even further west. In fact, so far west that we cross the, what is it? The prime meridian? The international date line? I forget. But basically, we're going from Vandenberg, launching west into the Pacific Ocean. So first thing is that delta L. I kind of want to just show you that real fast. Delta L is the longitude of the target minus longitude of the origin. And remember when we have a westerly longitude, we plug that in as a negative number. So let me stop color coding for a second. We're going to go negative 120.62 minus 167.73. Let's see here. Oh, yeah. Huh. Wait, did I switch those? I might have switched those. Apologies. I'm so sorry. I switched those. I misspoke. Happens to the best of us. And I'm not even the best of us. Okay.
Can you explain those coordinates one more time, please? I didn't really get those.
Yeah, actually. How's the best way to show this? Well, it's okay. Let me try and make my Earth. Here's the U.S. and South America. Wow, it's the worst ever, but it doesn't matter. We're launching from Vandenberg, which is on the west coast of the U.S. That was what that was supposed to be. And then Kwajalein Atoll is like a little island chain out there. So let's say our target is right exactly at that point. The latitude of something is how north-south it is, like how much north, how much south. So Vandenberg, as you can, even with my crappy picture, you can see it's a little more northerly than Kwajalein Atoll, which is almost right at the equator, right? 8.72 degrees north. And our missile is going to go flying something like that. So it's starting at Vandenberg, traveling to the west, right? That's the west, that's the east. So it's traveling westerly. Yeah. And the delta L, I accidentally switched to my, so I apologize, but it's the difference between the longitude, which is east-westness of the origin, minus the east-westness of the launch site, or the target, I'm sorry. So let me just write that out, and here's what that would look like. So the origin, what's the longitude of the origin? Well, 100, let's see. Oh, did I F? Hold on. I was right. I just needed to. Sorry, I'm getting stuff mixed up. I was right the first time. Anyway, what's the target? Well, the target is Kwajalein Atoll, and I mislabeled up there, so that's probably reason for confusion. This is always the risk of public math, but big L sub naught is the latitude of the origin. Little L sub naught is the longitude of the origin. Big L sub naught, or big L sub t rather, is longitude or latitude of the target. Geez, and this is the problem. There's so many L's. I'm not trying to excuse myself, but geez, it's hard to manage the vocabulary of them all. Big L sub t is the latitude of the target, and little L sub t is the longitude of the target. So the delta L is something we need for our cosine calculation. So let's see, the target is at 167.73 minus a minus 120.62. So our delta L, delta little L, 167.73 plus 120.62, 288.35 degrees. All right, cool. So now that we have everything labeled, it really just becomes a matter of, plugging it in. So sine of L naught, that's sine of 34.87. Sine of L sub t is sine of 8.72. Okay, plus cosine of 34.87 cosine of 8.72 cosine of our delta L, which is a big value. So cosine of our range angle, which is what we want, equals sine 34.87 sine 8.72 plus cosine 34.87 cosine 8.72 cosine 288.35. So it's 0.342. And of course, range angle itself, wow, oh, whatever, boom. Let me write that better. There we go. So we'll take the inverse cosine of that, and that'll give us our answer finally. $70.0021 degrees. Woo! We did it. Okay. After we got all of our labels sorted, does that make sense?
Sir, why is the for cosine 388.35?
Why is it the cosine of that value?
Right. Why was it a negative 120?
Okay. Yeah, so negative, so looking specifically right here, when you have a west longitude, the convention, just the tradition, basically the way you plug it in is as a negative number. So even though the problem just said, hey, it's 120 degrees west, well, cosine doesn't understand east and west. So east is positive, west is negative. Cosine understands that. So the delta L is the difference between the target's longitude and the origin's longitude. So that subtraction means that we took a positive number here and had to subtract a negative, which ended up making it a positive.
Okay, got it. Thank you.
For sure. Sweet. Okay. More?
Also, if it was the other way around, it was asking for the azimuth angle.
Mm-hmm. Yeah.
What would be the best way to go about that?
For me, I would just use the equation given, which is, so here, let's make it purple. Okay. You were talking about this, right?
So if it gives us the azimuth angle, it would, if we're asked to find the azimuth angle, it would give us the range angle.
That would be the fastest way for us to help you get through the problem. But if we said, hey, what just is the azimuth angle, instead of calculating range angle, we just said, hey, calculate the azimuth, you'd have to calculate the range angle first, because the azimuth equation is sine of L sub t minus sine L naught cosine range angle, right? So you're like, oh shoot, I have to find that first. But that equation like literally lives right above it on the equation sheet. So that'll hopefully trigger you to calculate that. But range angle is generally what I don't know. That's what I usually see asked for, just because that is a metric of how far the ICBM can go. But if you had to do it, that's how you would do that. That right there is azimuth. All right, sweet. Should we keep going here? I think the request was for the whole ballistic missiles part, so we can do that. All right, sweet. Then off we go. So then it tells us, and I mean, these look like they kind of build off each other, but Minuteman 3 has a burnout velocity, VBO, of 6.73 kilometers a second at an altitude, altitude of 1,100 kilometers. Calculate the trajectory parameter, or as we call it, QBO, for the Minuteman 3. Okay, why QBO matters, as a side note, is if your QBO comes out to be less than 1, then you can only really launch your ICBM the most direct way, the short way, as we call it. If your QBO is bigger than 1, that means you have a nice beefy ICBM that you could have the option of launching the long way around. So that's why it matters, kind of just for analyzing the weapon system itself. But anyway, that's just background info. So the math is really quick and easy. It says QBO is V squared VBO times RBO over mu. And we're launching this ICBM from Earth, so I'm going to assume we're going to use mu of Earth. Never have I seen a problem where we're launching an ICBM from Jupiter. Not sure we have missile bases on Jupiter. Coffee. Okay, so VBO they give us, but RBO, we're going to have to add raise to the Earth plus height. That's altitude. $74, $78. Okay, so when the main, that's supposed to be a 7. When the main engine's cut off, that means we are at an altitude, or not, see, even I said the wrong thing. We're at a radius from the center of the Earth of 74, 78. Okay, cool. Well, let's just plug and chug. Okay, 0 point, almost exactly 85. Ah, shucks. We can only go the short way with this ICBM because it's less than 1, but cool. Oh man, that's really quick, easy plug-in. Okay, then.
For Q burnout, are there units?
There are not. It's a ratio.
Okay, thank you.
You're welcome. Cool. So the Minuteman 3 has QBO of 0.85. Boom. We found that it's 0.85. So, joke's on them. Use the chart, figure E6 from the book. Oh man, to find the flight path angle for both low and high trajectory for a range angle of 70 degrees. Okay, let's see. Figure E6 from the book. I wonder, actually, you know what? Don't have the book on my iPad, although I wonder if I could get, well, in the interest of time, I'm going to pull it up off the homework instead. Or off of a homework.
For the final, will this table be provided to us, or
Oh,
will
yeah.
we? Okay, we won't have to do it the long way.
It has to be. There's no way. I mean, if you can memorize that, that's impressive. But nope, it's literally, it'll be printed out right like above the problem. And which is kind of lazy on the review that we didn't do that. In fact, maybe when I publish a review next semester, I'll go ahead and just drop the JPEG in there. I don't know why I didn't think of that till now, but there you go. That's me. Okay, so let me pull this up off the homework real quick. You know what? Actually, stand by 1 second. I'm just going to drop it in here. There it is. I did it. Okay. Thanks for your patience. All right. So I just mashed the 2 questions up there on the top and put the chart down here. Good. Assuming the Miniman 3 has a QBO of 0.85, which we actually proved that it does, use the chart. And I think this is the right chart. We'll quickly find out. But find the flight path angle for both the low and the high. So for a range angle of 70 degrees. We actually found that our range angle did have almost exactly 70 degrees. Sweet. Okay, so first thing we're going to do is, well, ignore question 37 for now, but Q burnout of 0.85. So use purple. So we're going to use this line, this blue line that curves down like this, right? And let's see, what we want to know is flight path angle, right? So the flight path angles are these red lines that kind of sweep down like that. So basically what we want to know is, where does our QBO line intersect 70 degrees? So let's see here. Let me draw it like this. Go blue and use a straight edge, actually. Go old school on this. Oh, oops. Here's our range angle. If you can see that. No, it's not working. Trying to draw this best I can for you. There's the range angle, right? That's the worst shape, but that'll work. Let's see here. All right, sorry for imperfection, but that sucks. Here, I'm just going to hand draw it like this. The range angle of 70 degrees has that dotted line basically that goes through that blue line that I just drew, right? So where does our QBO line intersect that? And it'll intersect it twice. So you put it this way, follow this around to right here. There's one place that it intersects, and then keep following it down around down here. That's the other place where it intersects. So what we're being asked for is, what flight path angle line is this first pink dot at? So like, here's 40. This would be maybe 41, 42, 43, 44, 45, 46, 47 maybe. It really is some eyeballing and guesswork, and that's okay. So our phi high looks like around 47 degrees. We can deal with that. And then we follow it all the way back down around. And this looks like it's almost exactly on a flight path angle line. What is that, 10? Comes down? Yeah. Phi low looks like about 10 degrees. So there you go. We've done that part of the problem. So again, after much ado, we just followed our QBO line all the way down to where it intersected our range angle line. And it intersects it twice, right? Once for the phi burnout low, once for the phi burnout high. And then after you've got those 2 dots, just you interpolate, in between, there's a flight path angle, maybe 49, 48, 47, or you can build up like I did from the lower, 1, 2, 3, 4, 5, 6, 7. It's very imprecise. That's okay. we give a ton of grace on this part of the GR because you're basically eyeballing and guessing. Okay. Now, using figure E6 from the book, still here. What is the maximum range for ballistic missile with a Q burnout of 0.85? Max range. QBO is 0.85. Okay, well, what I'm going to do is clean this up a little bit. Okay, cool. So, actually, I want to point this out to you. Here's the max range line. So if it asks you for max range, that's what this green line here is for. Okay. So all you really have to do, oh, whoa, I don't know how I got here. There we go. Is pick out your QBO line, right? So we have a QBO of 0.85. Follow it down. Follow it down to where it intersects the max range line. Right there. And then let's see where that comes down and intersects the x-axis here. Looks like it's almost exactly 95 degrees. So, whoa. Looks like the max or max range is about 95 degrees. Scrolling down, just double check. I think I'm pretty close, hopefully. Yeah. So like for feed burnout low, they got 47 just like we did. For high, and then feed burnout low, they got about 8 degrees, and I got about 10 degrees. So that's to be expected. We're eyeballing it, right? And then max range, they got 95.24. I don't know how you got that. I just got a 95 from the chart. So, yep, we're right on. Now, the last thing it asks for is what's the flight path angle required to achieve this maximum range? Well, just like before, right? You got flight path angle lines that are coming down through here, and this purple dot looks like it's almost right on top of that flight path angle line. Maybe that's like maybe 21. I'd say it's about 21. So phi for max range is about 21 degrees. Rise, right? Just kidding. Shoot, where I lost it. Come back. There we go. Fun. All right, so there's your ballistic missiles part of all this. What is next? What's next? Oh, ground tracks and COEs. And then number 16. Got it. I need to pay better attention to the chat. Sorry, I'm learning. Okay, cool. Let's go up to ground tracks. Don't know why I have to sound like a duck, but ground tracks make you sound like a duck, I guess. Sure, I'm glad I recorded that. Fine. All right. Got to laugh through the tears here, man. We're studying for finals in COVID times. Just got to keep laughing. Okay. So let's start with 10. Yeah, let's do. Okay. So you're given COEs. Make us a picture. Give us a beautiful sine wave picture. Okay. Annotate the delta n and put an X where you find the satellite to be. Okay. Well, the first thing I'm going to do is actually delta n. So how do I know delta n? Well, I actually have the information I need just in the semi-major axis. Well, how? Well, let me show you how. We don't have a lot of room here, but if I zoom in, I have more room. Okay. Period, I know, is how I can find my delta n. Wait. Why did I write that? I'm so dumb. Delta n over 15 degrees per hour. Blech. Stupid public math. Yeah. So if I can find the period, then I can find my delta n, right? Well, how can I find the period? I don't know. I also know that period is equal to 2 pi times a cubed over mu. So maybe I'll just find the period first and then find my delta n. And that's exactly what I'm going to do. A cubed over mu, 2 pi 12,793 cubed over 398,600.5. Equals 12,793 cubed by square root 14,400.23 seconds. This is an important distinction. This equation, this little period equation, gives you hours. This one gives you seconds. So you do have to convert between them. So let's see. Let's divide by 3,600. That comes out to be 4 hours almost exactly. All right. Well, now I can plug that in here and get my delta n. Ah. All right, so my delta n is 60 degrees. Here's my technique for this. There's multiple ways to do it, but I think this is the most common. All right, so look, each of these blocks from left to right is like 20 degrees worth, right? So each of these is a 20-degree block. Well, if I divide up 60 into a 20-degree blocks, that's 3 blocks. So let's see. 1, 2, 3. I just count from the right side over. There's 20. There's 20. And there's 20. So there's my delta n. Easy. All right, so what that does is that means that I'm not going to draw any shape that goes past my delta n, right? Because what delta n is how much of the Earth the orbit does not cover in one orbit, right? The Earth rotates too slowly underneath it. Okay. Next thing I want to do is, eccentricity is helpful just because that means we can draw an even sine wave that looks something like that versus like something weird. So that's helpful. Inclination of 40. That just gives us our north-south bounds. So like I always draw kind of a dotted line on how far north we can go, 40 degrees, and how far south we can go, negative 40. Oops, it's pretty bad. Let's keep that up. Okay, so basically now I have my left, right, and up, down bounds, and my eccentricity of 0 means that so what I usually do is just count how many blocks I do see in one orbit. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that means 15 over 2, so somewhere halfway in between, like 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and a half. Somewhere up right here. I shouldn't use an X. Let me not use an X. I'm just going to use a little dot to mark off for myself. That's kind of halfway. And the only reason I do that is so I can sort of draw an okay sine wave. Wow. I'm not the best at that, and you don't have to be either. It doesn't have to be perfect. We just have to know that you know that the orbit goes as high as up here, as low as down here, and doesn't pass the delta n. Okay, so now we get to the possibly a little bit tougher to visualize. Random 0, that is fine. That doesn't really help me much. Argument of perigee being undefined, that makes sense because we have no perigee. It's a circle. And if we have no perigee, then we have no place to measure true anomaly from. So we have this little u, which is argument of latitude, if you remember way back for GR1. Let's see. Okay. So basically, we don't even, yeah. All we have to do is start at the ascending node and track over to where our satellite's location is, because that's what U does. Starts at the AN, and you just measure around to where the satellite literally is. So let's use blue. Here's my ascending node. And of course, I mean, there's another ascending node over here. We're going to just use the one that's attached to the left side of the graph just for ease's sake. So if my U is 90 degrees, and this is, again, this is kind of an imperfect art more than a science, but if an orbit's 360 degrees, then about a quarter of it would be 90 degrees, right? There's 90, there's like another 90, there's a 90, there's a 90. So really you're just eyeballing, and we only have 90 degrees worth, so. U of 90 puts us about right there. That means our satellite is right there. Did we do everything the problem wanted? We labeled delta N, we put an X of the satellite's current location. Yeah, we win. All right, cool. Now let's go the other way around. Let's start off with a picture and get the COEs. Go back to red here. Okay, so remember how last time we took our A, we got our period in seconds, converted it to hours, and then we got our delta N. Now we're going to go the exact opposite way. We're going to take our delta N, get our period in hours, then get the period in seconds, should be a P, and then get our A, because that's the first thing that we want right here. So let's zoom in. How much of this orbit do we not see in one orbit? Well, it looks like 1 block, 2 block, 3, 4, 5, 6. And each of these blocks are 20 degrees, so 6 blocks times 20 degrees. Means we have a delta N, of 120. I like to mark that out. Delta N is 120. Okay, now let's actually do the math for it. I think that comes out to 8 hours, but let me just double check. 15. Yes, okay. Now, that's our period in hours. Period in seconds. It's going to be 8 times 3600. Means we have 28,800 seconds. Okay. Now let's use this period equation. Classic. 2 pi A cubed over mu. Let's solve for A. So A will be, let's see. I'll do it in a few different moves here. Period over 2 pi. I'll divide. Squared A cubed over mu. P squared over 4 pi squared. A cubed over mu. Okay, so that means that A is mu pi squared over 4 pi squared. P squared, I should say. To the 1/3. Let's plug and chug that. Oh. 28,800 over 4 pi squared to the 1/3. Oops, forgot to square. I'll raise that to the 1/3. Haha, and we get 27.4 kilometers for A. um, 307.4 kilometers for A. Hey, we did it. That's arguably the hardest part. So what can we tell about eccentricity? This is an interesting part of the problem here. So check this out. looking at this shape, hopefully you would maybe agree with me that this upper shape here is quite a bit bigger than this bottom shape here. Like we're covering a ton of ground up here in the yellow, not covering quite as much ground down here in the red. So what that tells me is the satellite's going faster in this yellow shape. So perigee versus apogee, like which one is always, you know, the satellite going faster? Well, perigee. The satellite will never be going faster than when it's at perigee, right? That's the fastest it'll ever go in a particular orbit. So my suspicion is that perigee is somewhere up here along this upper shape. Okay, let me get rid of the shapes a little bit so I clean it up. All right, so we're going to be in the upper area somewhere. And more than that, I can say that it looks like the satellite is traveling like mostly up here, and then it's starting to like bend over, and it starts to go even faster this way. And then it at this happens to be at this X, which marks the satellite's location, but looks like right about there is where it's going almost straight eastward, and it doesn't have any like vertical component, you know? So that's how I determine the satellite actually, its perigee is like, ooh, you know what? I'll use green still. Its perigee is right here in the middle of this upper shape where we're covering the most ground. Oops, I went straight to argument of perigee. Sorry, well, what I'm doing right now is argument of perigee. So again, we measure argument of perigee starting at the ascending node, which is right here, because that's where it crosses the equator, right? Like if I were to draw the previous part of this orbit, it would probably look something like this. But then right there at that green dot is the ascending node. So, and again, remember, just our satellite's going in this direction. That's always the assumption, unless you're told otherwise. So, starting at the ascending node, again, you know, that'd be 90, that'd be 90, that'd be 90. That's that type of thing. So from the ascending node to where perigee is, I almost should have labeled perigee. It's about 90 degrees. So that means our argument of perigee is 90 degrees. True anomaly is measured from perigee to where the satellite is. Oh, well, shoot. The problem, before I marked on top of it, oops. Doggummit. My wrist always keeps hitting it. Sorry. So the X that they told us is here under where my perigee dot is. So the satellite's right on top of perigee. So that means, well, okay, well, that means that it's 0 degrees away from perigee. There you go. So now let's continue to look at the eccentricity part. So if you guys remember when I was crazily drawing different colors, right, it looks like we're covering more ground up there than down here. The fact is this is not a symmetrical shape. And if it's not a symmetrical shape, then you can be confident that your eccentricity is somewhere between 0 and 1. That's all you can really say. All you can really say is, well, I know it's not a circle because a circle would have something more symmetrical like we drew for the last problem, right? But it doesn't. So this orbit is somewhat elliptical. That's how you can tell, is those two shapes do not look like they're equivalent. Inclination, that's very simple. That's exactly how we determined it from the previous problem, right? You just see how north the orbit goes and read right off the graph. So that looks like there's 40, there's 60. So it looks like it's right in between, like maybe 50. And then RAN, here's some free points. Right, unknown. Don't write undefined. I cannot tell you this enough. Don't lose those points. RAN is defined. I mean, there's definitely a RAN for this orbit. We don't know what it is from the map. You just can't tell from a map. So there you go. There's ground tracks.
I have a quick question, sir.
Sure.
If the shapes were on the opposite side, so let's say it was smaller on the upper end and bigger on the lower end, like how would you determine where argument of perigee is at as well?
Oh, I see what you're saying. Okay, so let's say this is going to get busy, but that's okay. Like that it was something like this, and then down here was like that.
I can't see anything.
You can't see anything?
Yes, sir. Yes, sir. Yes, sir. I see it now.
Okay, cool. Yeah, it's probably taking a while with the live stream, but the shape up here, I'm guessing you would believe is a lot smaller than down here. So you're covering a lot of ground down here, I should say, in the red. You're not covering as much ground up here in the purely yellow. So that would mean that your perigee, let's see. So we know we're down here somewhere for perigee. Here it looks like it's mostly going like vertically, even in my crappy drawing, and then it starts to trade its vertical up and down velocity for an easterly velocity, and it looks like the, what would you say, the most extreme easterly velocity is like right there, right? And then it starts to again trade horizontal velocity for vertical velocity. Does that sort of answer your question?
Yes, sir. So would true anomaly still be 90 degrees? Or
I see what you're saying.
Yeah,
in this
argument
problem,
perigee.
let's see. If everything else was the same, let's see. Argument of perigee would be, so our ascending node would still be here with the purple orbit, and we would go, there's 90, there's 90, and there's another 90. So in this case, our argument of perigee would be 270, because that little dot's supposed to be perigee. And then let's see, and let's say that the satellite is still at the black X, or, oh, sorry, I guess with our orbit, it'd be right here with this purple orbit, right? That would mean that you're going to, from perigee, measure where the satellite is going from left to right. So there's 90, there's another 90. So in that case, our true anomaly would be 180. Woo!
Thank you, sir.
Wow. You're welcome. Yeah, you're welcome. Okay. Predicting orbits. All right, that's what's up next. Let's see. Before I launch into that, can I have a quick 5-minute break? I'll be back at 3:45 right here. And you know what? I'm going to add another one on top of this because I would like you guys to be able to see both versions of this problem. They're different enough that, well, they're different. So, okay, given the following, where will the satellite be in 9 hours? And it's even nice enough to tell you that means true anomaly final is what they want. It's not always that nice. So yeah, we want true anomaly final. Okay, great. Here. Oops, sorry, I have to wipe my iPad off real quick. Got water on it, jeez. Okay, where will the satellite be in 9 hours? Gives us some major axis, eccentricity, inclination, RAN, perigee, true anomaly, initial. Okay, well, as nice as it is to have these things, we don't need inclination, we don't need RAN, we don't need arc pair. That's just extra flavor text, I suppose, lore, if you will. Okay, so here's how this is going to go. We're going to start off with our true anomaly initial. We're going to use that to get eccentric anomaly initial. We're going to use that to get mean anomaly initial. We're going to plug that into the time of flight equation, and hopefully out of that get a mean anomaly final. Then we're going to come over to eccentric anomaly final, and this is going to take some iteration. That's okay, we'll figure that part out. And then whatever we converge at for our eccentric anomaly final, we use that to find true anomaly final. Easy peasy, lemon squeezy. No one should say that. Okay, but there you go. That's what we're going to do. First things first, put your calculator in radians. This is one of those problems where it has to be in radians. I'm doing that right now. I think it's shift mode 4 for y'all, or shift mode 3, I forget. But, okay, cool. Let's begin. Let's go into this part of the equation sheet. You can hear it crinkling. I have my equation sheet out. Let's find eccentric anomaly initial. So, equation sheet tells us that the cosine of eccentric anomaly of any kind, and we'll put a little I for initial, is eccentricity plus cosine of true anomaly initial over 1 plus e cosine true anomaly initial. Okay, so let's plug and chug that. Eccentricity of 0.4 plus cosine of true anomaly initial, which was 180. I'm going to show you a trick here in a second, but first I'm going to prove to you that it works. 1.4 cosine 180. And instead of using 180, you know what I should do since we're in radians here? Should have done this at the beginning, but that's pi. Okay, cool. So cosine pi over cosine pi. Alrighty, 0.4 plus cosine pi divided by 1 plus 0.4 cosine pi. Inverse cosine of that is pi, or 3.1416. And again, I also recommend, that's an important thing, and then also I recommend keeping 4 decimal places throughout the entire problem. It's really important. Okay. Sweetness. All right, let's keep going. I predict the mean anomaly initial will also be pi, and I'll show you why in a second here. But mean anomaly, our equation sheet tells us, is eccentric anomaly plus eccentricity. Oh, why am I dumb? That's minus. There we go. Sine of eccentric anomaly initial. There we go. All right. So what is this? 3.1416 minus 0.4 sine 3.1416. Wow, no, that is not what eccentricity is. It's just 0.4. Public math gets hairy sometimes. All right, 0.4 sine of that. Also pi. Ta-da! All right, so here's the trick. If your true anomaly initial, here, let me just draw it up here. So true anomaly initial is 0, then its brothers, eccentric anomaly and mean anomaly, are also equal to 0. Or if it's pi, true anomaly initial and mean anomaly initial are also equal to pi. And we proved that. True anomaly initial is pi. I didn't have to do the math to go through it, but we did prove that they're all pi, right? Its brothers are both pi. So anyway, there you go. That's a little trick to speed things up. But if you ever forget that, or just kind of fed up with trying to remember which tricks are which, then the math always works. And time's not a factor on the GR, right? Or for the final, rather. It's you won't find yourself rushing, I don't think, on the final. At least in the times that I've administered it, I've only had one person, I think, stay till the very end, and it wasn't because they were rushing. It was because they finished, and then maybe like the 2.5 hour mark, and they got up and they got, we went to the bathroom and got some water, and they came back and they kind of perused it and checked their final through again, and they got up again and came back. They do what I used to do, and which was that, like, I would try and get through the GR as quick as I could, then come back and check it a couple of times because I guess I'm obsessive that way. But anyway, all that to say, you'll have plenty of time. You can always rely on the math. Now let's keep pressing. Alrighty, mean anomaly final. All right, we need to find mean anomaly final now because we found true, eccentric, and mean. So our time of flight. Time of flight is given to us, and it's disguised kind of. Like, where will the satellite be in? That means time of flight. Where will the satellite be in 7 seconds? Where will the satellite be in 9 hours? Yeah, that's what time of flight is. We need to convert that to seconds, though. Hey, there we go. 9 times 3600. Yeah, 32,400 segundos. All right. So mean anomaly final, they tell us, is in this equation where you have to subtract mean anomaly initial multiplied by this thing n times time of flight minus 2k pi. All right. Well, for right now, we're just going to kind of put a little blue line through it because we're going to come back to it in a second. We're not going to use it right now. And then n, so we have our time of flight, but what's n? Well, n, I'm going to put up here because we're running low on space. It's called mean motion, and it's the square root of mu over a cubed. This is going to be a ridiculously tiny number. It always is, and that's okay. Basically, it's very small. Nope, what am I doing? A is 12,000, they say. Okie dokie. Cubed. Let's find one where everything's undefined. Oh, this here, right here. Rand's undefined, argument parity is undefined, true anomaly is undefined. Oh man, these are actually the best kind, believe it or not. They end up being quite a lot simpler, but okay, let's just start off at the beginning and go down as we always do. So, semi-major axis of 15,000 kilometers. What does that tell us? Not much. Not really helpful. Eccentricity of 0. Oh, that flags me to know that this is a circular orbit. Okay. Inclination of 0. Ooh, that's also unique, right? Because that means equatorial. Now, if I'm just orbiting around the equator, that means I'm never going to hit the poles. Ever. Never going to touch them. Wow, why did I fill that in? I meant to get rid of it. There we go. Never going to hit the poles, which means I'll never touch the North Pole. I'll never touch the South Pole. And because the k-axis runs through the poles, I'm never going to hit either the k-axis. So, wow, that just, a lot of stuff just dropped there. Okay, prograde versus retrograde. Well, how do I know? Well, prograde is anything between 0 and 90, not including 90. That's pro. Space. Retro is anything between 0 or 90 rather, not including 90, and 180. What's our inclination? 0. So that falls squarely within the prograde category, which means it cannot be retrograde. Okay. Now everything else is undefined. We're gonna have to go to the picture. So this is a picture of our orbit. You know, actually I have more space. I'm gonna be even bigger. Whee! Oh, that was bad. Okay. There we go. That'll work. Okay.
Sir, if it's equatorial, doesn't that mean there's no ascending or descending node?
That is true. Yeah, we'll get there. I promise. That's very true. So okay. So what Gega is talking about here is, and what I'm going to try and draw, is the orbit view here. Because our inclination is 0, like we're basically just orbiting around the Earth. Right there's I always draw the ice caps. My class can tell you, right? So I kind of know where I am. And I draw, you know, a J-axis out here and an I-axis out here. But yeah, because basically this orbit, if we're looking at it from the side, right, here's continents and ice caps, and you know the equator comes along right here. This orbit is literally just like going around the equator. So when we draw the edge on, or sorry, basically the perpendicular view of the orbit, which is what this is down here. Yeah, we're basically looking directly from the top of it. Just happens to be for this problem. So yeah, and Giga is exactly right. This is, you see that this blue orbit here doesn't rise above the equator ever. That's what equatorial orbits are. They just stay around the equator. And the definition of a node is where it rises above, you know, from south to north hemisphere or north to south. It never does that because it just sits around the equator the whole time. So you can get rid of those. You know what else you can get rid of while we're at it is perigee and apogee. Why is that? Well, we're circular. Circles don't have perigee or apogee. They're all equally close and far away. Right? So really all we're trying to determine is our spacecraft on the I or the J or not at all? So from the I hat, basically are measured around to where our satellite is. That's what this is, true longitude. You measure that again from I hat around to where the satellite is. So starting at I hat, let's give ourselves 180 degrees worth of little L. There's 90. There's another 90. So it looks like it's on the opposite side of positive I. So this would be negative I hat. Here's our satellite. Being on negative I hat still counts as part of the I hat axis. So we can say it's on I. looking at our picture, I mean, here's J, here's negative J. Looks like we're not on either of those. And besides, we know actually by inspection, if we're on one of the axes, we can't be on either of the others at the same time. So what do we decide after all this? Well, it's a perfect circle. It's inclination of 0, so it's on the equator. And it's currently sitting on negative I hat, so that counts as I axis. Sweet.
Sir, if we're doing this on our whiz wheel, is that L acting as the RAN, or what is that?
So, and remember, RAN would be where it's orbiting, or whether rather, let me put it this way. The orbit only has a RAN if it's like descending, you know, or let's see, on the others, I guess the way I drew this, the ascending node would be over here on the other side, but it has to have an inclination that's greater than 0, so it can actually cross from the northern hemisphere to southern or vice versa. But our orbit, I tried to draw in blue, it doesn't rise above the equator ever, right? It doesn't cross from the northern hemisphere to the southern hemisphere ever. It just stays on the equator the whole time. So we have no RAN. So this true longitude is really a replacement for both perigee and true anomaly. Because the trick about a circle is there's no perigee or apogee. So that means I have no perigee to measure true anomaly from, because that's where I start measuring true anomaly from. So you're like, well, okay, shoot, or where do I measure my satellite's location from? It's like, well, the only thing that's really left is I hat, which is that fixed point in space, right? Pointing off towards the first point of Aries on the vernal equinox. That's really the last fixed point you have to measure from. So starting there, you can measure around counterclockwise to where your satellite is. So it basically fills in for perigee and for true anomaly.
Thank you, sir.
You bet.
Sir, can we
Okay.
go over really quick the special types of, like, for example, longitude and then also mu and the other special types of equations on box problems really quick?
Yeah, actually, yes, we absolutely can here. So let's see. I will write these down here. And I'm going to pull something up real quick. Alrighty. Oh, where'd my pencil go? Oh, there it is. Okay. So U, which we used in a previous problem. Here, we'll just write them all down here. It's U, and that is called argument of latitude. So you use this when you have no perigee. Sorry. Use when you have a circle. Thus, actually not i.e. That's probably not the wrong. Thus, you have no perigee. I cannot spell today. How you use it. You measure from, let's see, how's the best way to put it? Basically measuring from the ascending node around to where the satellite is. Measure that around to the satellite's location. Why do you do that? Well, this is when you do have, generally you have some inclination. Actually, you have to have something greater than 0 for your inclination. So you do have a node. You have an ascending node to measure from. And that is preferable to measuring from I hat, which we had to do for the previous problem. So ascending node around to where the satellite is, that's called the argument of latitude. And it's essentially a replacement for, again, for perigee, because you have eccentricity and you have 0, which means no perigee. It's a circle. Let's see here. Capital pi, big pi, has like a straight top. It's called longitude of perigee. This is if you have no ascending node. So this is used when inclination is 0. Thus, you have no ascending node or descending node. How do you use it? You basically start at I hat, measure around to where perigee is. And then from perigee, you can get true anomaly and measure it from there. But so this is, let's see, I should probably put this. Argument of latitude is essentially a replacement, if you will. What's the best way to put it? I guess it's a replacement for perigee, yeah. And then longitude of perigee is a replacement for your ascending node or descending node. Okay, cool. And then I'll just put this last one in blue. Last one is called, it's a little lowercase cursive L, and that's called true longitude. And that's the one I believe we just used. 8,000. So 8,000 times 400 pixels in one image. And that gave us 32 or 3,200,000. Sorry, I had to kind of replicate this. Pixels per image. So how many bits? That's what I was trying to get to before my iPad decided to go nuts. I'm broadcasting to you on my iPad, that's why. Okay, so how many bits are in each pixel? Well, it says there's 12 bits in this case in each pixel. So that'll let our pixels cancel out. And that equals 3,008,400,000 bits per image. All right. Now we kind of shelve that for a second, just put it off to the side. Again, I'm changing this to megabytes to make it consistent. Well, how much storage is 75 megabytes? Well, you guys know, like your phone has many, many times that amount of storage. But there are old satellites out there that didn't have that much storage, so this is a thing for sure. But 75 times 10 to the 6th bytes is how many that is. Million bytes, megabytes. And hopefully from that lesson, I think actually, yeah, I did the CDHS lesson. Haha, no big deal. Every one byte, there are 8 bits. Just a computer comp sci kind of a thing. So that means that our storage is equal to.
Sir, just
Yeah.
a quick note. This one says 12 bits per pixel for this one. Oh, sorry. I thought you were doing bits per pixel. That was my bad.
Oh, no. Sorry. Yeah, sorry. Like we do run out of space here. I'll divide it out like that. Yeah, so 75E6 times 8. This gives us 6 times 10 to the 9th bits. Okay. So what we really want is, I guess this is bits per what, hard drive? This is bits per our hard drive. So 6 times 10 to the 9th bits on this hard drive. HDD is how computer nerds like me abbreviate hard drive. Over 38400,000 bits per image. That division allows the images unit to come up here and the 2 bits cancel out. So let's see. Divide that by A and I get, can't store very many images on this one. I get 15.625 images. Now something to watch out for is what if the problem said full images? Well, if it said full images, then you would just truncate this and say 15 full images. Cool. There you go on that one. Alrighty.